going to talk about where functions are increasing and decreasing, or where they're constant. Okay? So let's think about what it means to be increasing and decreasing. When we are increasing, that means our y values are getting bigger, right, as we go from left to right. Right? Okay. If we're decreasing, our y values are getting smaller as we go from left to right. And if our function is remaining constant, our y values are remaining constant, right? Okay. What we're going to be able to do is we're going to use calculus to figure out where our function is increasing and decreasing. Because tomorrow that can tell us, cool. Well, what I think might be cool. You may not think so. What? It's called the first derivative test. Okay, so now, what does it look like if our function is increasing? Did everyone hear Nate? Say it again, Nate. If our function is increasing, then our derivative is positive. We talked about that before, right? Okay, all of these tangent lines have positive slope. Okay. So if our function is increasing, our derivative is positive. What about if we are decreasing? Then all of our tangent lines have slopes that are negative. Our derivative is negative. Look at all of these little tangent lines that I can draw. All of those slopes are negative, right? What? I could have. What?
It is the instantaneous rate of change of any point for the slope of the tangent.
Great job, Brady Maker. You have that memorized now. Okay. And then, if we are constant. So what does that mean about our derivative?
It's equals.
If we are constant, then our derivative is 0.
I like this only having 10 slides.
Yeah, no.
Why do you guys
I always look at
It's on the domain A and B, right?
A to B.
Is A and B inclusive?
No, that's why it's open parentheses. Okay, that's a good point. Do you see how we have open parentheses here? Because at a change, remember our critical value could be our derivative could be 0 or undefined. So we are always going to write these as open intervals. Why aren't you guys listening? This is important. Okay. When we talk about increasing, decreasing, and constant intervals, we're going to write them as open intervals. Okay? Because where we have changes in direction, that is where we have those critical points, where our derivative is either 0 or undefined. Okay? So let's look at this picture right here. Here is a function. Where is this function increasing? The open interval, right? Where is this function decreasing? I would say that's 3. And where are we constant? So you want to include one?
Yeah, why would you include the?
Isn't at that point, though, isn't it?
Well, what's true about the derivative here?
Doesn't make sense.
It doesn't exist, so we know we can't do
But
it.
it does exist at one.
-3, it exists.
You're telling me that the derivative exists right there at the endpoint?
Never mind, forgot.
Okay,
But one, it doesn't exist.
what?
Doesn't derivative exist there and zero?
We would have to know the equations to tell whether that would exist or not.
Yeah.
Okay?
Why don't the endpoints work?
You can't find your.
Well, because, can you come up here and draw the tangent line at that endpoint?
Can't you just have it like, yeah, can't you just have it like go through the endpoint, like touch it? Just like the slope of the line.
Well, see, it's the same problem at like this corner here. You know, we don't really know where to place it. Okay, at an endpoint, because, okay, let's say this, can you really tell me that at that point we're increasing? That's where we're beginning, we can't really say that we're increasing there, you know what I mean?
Yeah, like.
Okay, so we can obviously look at a graph and figure out where we're increasing and decreasing, right? Yes.
Some programs are arbitrarily calculated derivatives from like if you want, like, certain programs will calculate where it is in the spectrum. Like arbitrarily, you can put a video on an XY axis, and then you'll have programs that track points at certain places that you put it on. So if you are there programs that do that with derivative lines, so they just calculate derivative lines at any point, so you can like get the derivative really sneak. You know what I mean?
If we had an equation, yes. I don't know. Without an equation, I don't know how to, I don't really know what to track this. Okay, we can make a snake equation. Yes.
What's the thing above the arrow, above the thought?
That's an X. Like for the x-axis,
It's like,
Carter.
It's like, like 3D objects.
Yes, we can do derivatives in 3 dimensions. No, we're not going to. Okay, so here we go. We are going to use calculus to find intervals of increasing and decreasing. You can look at a graph and do it, right? But what if we don't have a graph? What if the graph, you know? Okay, graphing it, yes, to a certain extent we can do, but we have to know where those critical points are because that's where we could be changing direction. Okay, so the first thing you're going to do is find critical points. How do you do that? Find a derivative and find where it is. 0 or undefined. That tells you what your critical points are. Remember, critical points could be where we're switching direction. And if we're looking for increasing and decreasing, those points of switching direction would be important, right? Yeah? Okay, so when you have your critical points, you're going to draw a number line with your critical points. Okay, and if you have 3 critical points, it can be a number line with 3 dashes on it. Okay, but what we need to do is we need to test our intervals. Are we increasing or decreasing on these intervals that are being broken up by our critical values? So to do that, you are going to test values in f prime. Okay, you're going to test your values in the derivative to determine whether your derivative is positive or negative. Interval. Okay, from that sign chart, we can then write our intervals of increasing and decreasing.
Sign like in cosine, or just like the sign up there.
Okay, so critical values mean our derivative is 0 or undefined. So those are places where we could be switching direction. So we're going to place those on a number line, and we're going to decide in between critical values, are we positive or negative on our derivative? Because if our derivative is positive, what does that mean? And if our derivative is negative, what does that mean? Right, so we are decreasing. That's the word we're going for. Yes.
What if it's like a constant, and that would be enough, if you get 0?
Yes. Yes. In the interval, if you get a 0, then it would remain constant. That is a good point. Okay. All right, so we're going to start off easy. Okay, so I want to find intervals of increasing and decreasing. Anytime you see the word increasing or decreasing, you need to think of the derivative. Okay, because that's what's going to tell us whether we're increasing or decreasing. So we need to find the derivative.
What is open?
Open. Close, brackets, open, parentheses. Okay? So what's our derivative? Okay? And what are we going to do with our derivative?
What's our, do we not have an interval?
Set equal to 0.
We do not have an interval anymore. It's the entire function.
Okay.
Set it equal to 0. Help me out.
Plus or minus.
Plus or minus 2.
Under what domain?
Entire domain.
Oh, we're plugging it, my bad, okay.
This is a polynomial, so all real numbers, right? Okay. All right. So you're going to place your critical numbers on a number line. And this is going to break up into 3 intervals. Okay, so we're going to pick points to test. So to the left of -2, what would you like to plug in? -3, and we're plugging into the derivative.
Do we not need to find our critical value points?
We did.
Do we not need to find the points, like the actual points though?
No, not right now. Not right now. Tomorrow, yes. Right now, no. So let's plug in 3 to our derivative. Excuse me, -3. Won't matter, but 15.
Yes.
I feel like 3 times 9 minus 12 is 15. Well, that doesn't seem right first. So it's positive, right? So I'm going to put a little positive here. Okay? Because that interval, our derivative is positive. All right? Now, what would you like to test between -2 and 2?
0.
0. And when we plug in 0 to the derivative, we get -12. So our derivative is negative in between -2 and 2. What? You tested intervals, but obviously not with derivatives. All right?
So it's the same thing, but we're just drawing the derivative.
Yes. We're still looking for those intervals of positive versus negative. Okay? And then what do you want to test on the right?
7.
3.
And when we plug in 3 to the derivative, we get,
15.
which is positive. Okay? I don't necessarily need to see your work for these signs. I understand that some of you can do it in your head, but you're more than welcome to include it if it helps. Okay? So now, if I'm asking for intervals of increasing and y -infinity to -2. Because our derivative is positive. Where else? 2 to infinity, because our derivative is positive. Okay. And where are we decreasing? -2 to 2 because our derivative is negative. If you are ever asked to justify increasing or decreasing, you better tell me about the sign value of the derivative. If you are decreasing, that means your derivative is negative. Yes.
Are you sure that from negative infinity to 2 and 2 to infinity is united like that?
Yes. Because both intervals we have a positive derivative.
And that means they're united.
Well, right. So we're increasing from negative infinity, -2, and 2 to infinity.
Okay.
So you grab it on our calculator.
Is this in the recording?
Yep.
Yep.
The Royals won.
Spoiler alert.
Spoiler, yeah.
Okay, what was our equation?
Cube minus
X
12
cubed
x
minus
X cubed minus 12x. What? Oops.
So are we finding where the derivative is positive, negative, positive, or?
Yep. We're the derivative. Okay, so you can see we're increasing from negative infinity to 2, as well as negative infinity to -2, as well as 2 to infinity, because that's where our derivative was from. Well, we have to use calculus to get that 2 and -2. Okay? And we're going to have to do this without our calculator at times.
In case you forget it at home, you have to do this.
Okay? Now this. Do we know how to graph this? We don't know how to graph this.
Calculator does though.
I knew somebody was gonna say.
Okay? We need to be able to do this without our calculator. Okay? First of all, what is the domain of that function? It is all real numbers. Why?
Cube roots.
Just squared.
Cubed root, so it doesn't matter what's underneath it. Okay? If you only had a domain of, like if your domain was 0 to infinity, you could make a number line that just started at 0. Okay? 0 would be one of your critical points if that's where your domain started. Okay? But you wouldn't have to worry about. So here we go. If we're looking for increasing and decreasing, we need to take the derivative. Help me out.
2/3 x squared minus 9 -1/3 times 2x.
Times chain rule. So power rule, then chain rule. Excellent. Let's make this look a little prettier. Thank you. How do we make this look prettier? Your mumbles have been very helpful. Does this look okay? And what do we need to do with this? Okay, let's figure out where our derivative is 0. That means 4x is 0. X equals 0. Let's figure out where this is undefined. And so what do we do? Set. Okay. So how are we going to solve that? Divide by 3. Then what? Instead of cube rooting, you cube it. Okay. So now we have 3 critical points. Let's get to it. What do we want to choose to the left of -3? -4, sure. So when we plug in -4, we have -12 on top over 3 times, what kind of number is this going to give us? It'd be -16, it'd be 16 minus 9, right?
The top would be -16.
Well, then,
All those keywords.
okay, what about this? This would be 16 minus 9 to the 1/3, right? So what kind of number is that going to be?
Yeah, they're gonna go up.
We'd have negative over positive, wouldn't we?
Ooh.
Okay, now what do you want to test?
Oh.
So we'd have -4 over -8 to the 1/3. What kind of number is that going to be? So our derivative is positive in that interval. You find me the other 2 intervals. Please. John, what's the derivative between 0 and 3?
Positive? Or, oh, the derivative,
Did you plug into the original?
yeah, no, yeah,
Okay, we got to plug into the derivative. Okay? Jimmy, can you help us? Negative. Try plugging into the derivative, see if you get negative there. Okay? Aaron, 3 to infinity.
Positive.
How do you feel about that? Okay. Yes.
Looking at like a negative, positive, positive, negative, could you write that as in like it's decreasing from this over here and then it's increasing from these 2 points, like combine the 2, or?
That's a good point, and let us finish this problem, and I will answer that, okay? Because I know exactly what you're talking about, and that is a good question. So first of all, where is this one increasing? -3 to 0, and 3 to infinity, because what? Because the derivative is positive. We are decreasing. Negative infinity to -3 and 0 to 3 because with a little bit more enthusiasm because how can I work with this? It's Monday. Come on, have some pep in your step. Hey, I sit up and watch the Royals game, and I'm up here being peppy for you. So you can at least meet me halfway.
That's the only reason you picked it.
And is it even possible to have, like, negative, positive, positive?
Yes, it is. It is possible to have a sign chart like this, and I think that's a good question. So Josh was asking, in this case, how would we write our decreasing intervals? Well, 0 is a what? Critical point, which means our derivative is 0 or undefined. So it cannot be included in any interval. So you would have to say we are decreasing from -1 to 0 and 0 to 1. It can't be across the entire interval.
Changing direction, it's still.
It's just, it's not,
Well, what's probably happening is there's like a vertical tangent, so, so increasing, and then it keeps increasing. That was a horrible drawing, but do you please? Or, because we're still increasing, right? So we have a horizontal tangent there, but we're still increasing. Or, I guess this was decreasing, but,
Well, that would have been,
so reflect it.
but that would have been.
Can you just reflect it and draw it? For a better picture? Yeah.
So here at this point, we have a horizontal
Oh, just
tangent.
one,
Because that was a little long.
Would you like to do another example?
I think we're good. Skip it. Wait, so you plug
Oh,
in
that one
the
would be so
derivative?
easy.
I want you to find me the derivative.
Alright. Okay.
I'll climb myself.
That was the bug.
Like nose, bug. Give me great hair.
Just take the derivative. That's all I want you to do. Take the derivative. What rule are you using?
Oh, frick.
So, if that's squared, one squared, just that's squared, or just x to the fourth, Dude, it's actually really hard to win. Yeah. I did that like.
Can't do no hard on both sides.
No, it's so hard. Well, yeah.
Have your own papers. Get out of here.
What did you get, Brady?
For the derivative?
Mm-hmm.
Didn't you just write it up there?
Is that all you did?
Simplified. Okay, let's see. It'd be 4
So-
to the fifth.
Is simplifying going to be important here?
Most likely.
So it'd be 4x to the 5th minus 8x to the 5th plus 2x.
I mean, unless you try
Or
that again.
2x to the 3rd
there,
plus 2x
minus.
minus 2x. Oh, yeah, okay. Over x to the 4th.
So 2x to the 5th minus 2x over x to the 4th. Yes, you can we factor out an x up above? So 2x to the 4th minus 2 all over x cubed. All right.
Take the 2 up too, or then that. Yeah.
You could, yes. Would you like to do that?
Yes.
Why would you touch the, you took out that?
Mm-hmm. Okay, so now our critical values. Where is our numerator? 0. 1 and negative 1. Where's our denominator? 0. Okay, so if we plug in like negative 2, what if we plug in negative 2? Is our derivative going to be positive or negative?
Oh, negative.
because this would be a positive number,
That would be,
this would be negative. How about, what, negative a half?
that's good.
What would happen in the numerator? It'd be negative in the numerator, right? Negative in the denominator. Do we see that? Okay, 1/2.
That's still positive.
Well, this would be positive up here, or this would be negative up here, wouldn't it?
Oh, yeah.
But then this would be positive downstairs.
There's zero.
And then if we plug in 15,
Whoa, two.
What?
Geez, you got higher.
so we are increasing from -1 to 0 and 1 to infinity because,
The derivative is positive.
thank you, we are decreasing
If you change it at those points are positive.
We're decreasing from negative infinity to -1 and 0 to 1 because the derivative is negative.
Yes, homework. Got it. Agreed.
Is this not the right assignment?
No, we just have some of the same ones assigned. Yeah, last time we did 3.
But it wasn't from page 183.
Oh, yeah.
Whew, okay.
It just looked sick.